Hi everyone, so in the previous video we have discussed how to relate work and energy. So we have arrived at three different relationships. One is the work energy theorem, which relate the total work done with the change in kinetic energy. Then we also have work done by conservative forces, which is equals to the negative of the change of potential energy. And the last one will be the work done by non-conservative forces, and it's equal to the change in mechanical energy. So we learn three different relationships between work and energy, and we are going to try to apply it in this question over here. Okay, so it says here that you have a block of mass 2 kg. So I assume this orange thing here represents the block. Then it moves with a velocity v towards a spring. So it's indicated by this arrow over here, shown in the figure below. The block compresses the spring by 2 cm. Well, this is not being labeled in the diagram, so probably later we need to draw another one to indicate it more clearly. Given that the force constant of the spring is 1000 Newton per meter, so force constant is the spring constant for this case. So spring constant is K, so K equals to 1000 Newton per meter. Then determine the velocity of the block if the surface is smooth and if the surface is rough with frictional force of 3 Newton. Well, like I say, probably let's start with drawing out the things first. Usually when I do a question, my first step will be trying to visualize the whole situation first. So the initial situation will be something like this. Okay, if you draw exactly like how the situation looks like in the diagram, then it will be something like this. So your m will be, your mass will be equals to 2.0 kg. Then you'll be moving with a velocity of v. Then this will be the equilibrium position. So then after that it says that the block compresses the spring by 2 cm. If it compresses the spring by 2 cm, you can assume that later the spring is shorter because compress causes spring to be shorter. Then we can safely assume that the block is in contact with the pad over here. The block must be in contact with the pad over here, or else it will just go back to its original length. The block is the one that compressed the spring, so the block has to be in contact with the spring. So with that said, we can say this and this. If you check on the distance, it should be 0.02 meter. I transform it from 2 cm. Okay, so I think, yeah, we still have things to label here. We can label about the spring constant, which is K equals to 1000 Newton per meter. So after labeling everything, let's try to figure out what kind of concept that we need to use for this question. For chapter 5, I usually split into 5 main concepts. The first one will be work done by individual forces. So this is the one where you learn about Fs cos theta. Work done by individual forces, if the force is constant, then you can use W equals to Fs cos theta. But if the force happens to be changing, force is varying with distance, then the only way in our syllabus will be to find the area under the Fs graph. Okay, so that's our first concept, work done by individual forces. The second one will be work energy theorem. Okay, this is my way of thinking about it. You might see things differently. But for me, I usually split into 4 different concepts. This one is the work total equals to change in kinetic energy. The third one will be principle of conservation of energy. To be more precise, it should be principle of conservation of mechanical energy. Technically, in our syllabus, we are trying to conserve mechanical energy. Actually, those equations that we use, we are actually conserving mechanical energy. And the fourth one, it will be power. So conservation of mechanical energy, so sum of mechanical energy initial equals to sum of mechanical energy final. And power, there's many formula. You can have power work done over how much time has elapsed, or you can have the work, if it's work total, then you can change it to change in kinetic energy over time elapsed. Or if you are being a bit adventurous, you can change it into FV. But all these things are average power. Then you also have instantaneous power, which is equals to the force at that particular moment and the instantaneous velocity. Yeah, those are a few types of formula for power. So these are the four main concepts for chapter 5 in my opinion. Okay, you might see things a little bit differently, but this is my opinion. So for this, we have to choose which concept to use. So the way I think about it is, if you have spring, right, then usually in chapter 5, if you see spring, it will be related to elastic potential energy. So elastic potential energy means by you have to use a concept which is related to energy. So if you want to use a concept which is related to energy, it's most probably not concept number 1, because concept number 1 is still talking about work. It does not relate to energy. Then work energy theorem might be a candidate, but if you look over here, work energy theorem only limited to change in kinetic energy. For now, in this situation, we have elastic potential energy, so just talking about kinetic energy will not be sufficient probably. So this might not be the concept to go. Then the next one is principle of conservation of mechanical energy. It seems like there's only mechanical energy here, but remember, mechanical energy is related to kinetic energy and potential energy. And potential energy, it can be elastic potential energy. So this is a good candidate to be used for this question. The last one is power. Power, usually we use it to say the rate of work done. So it means by you have to somehow relate it to time, either using the time elapsed or what's the velocity. Something has to be related to time. But if you read this question, everything is not related to time. It's talking about force, it's talking about distance, it's talking about spring. So there's no concept of time in this question. So in that case, we cannot do anything with this concept of power. So we have identified our principle of conservation of mechanical energy to be our concept to be used. So conservation of mechanical energy. Conservation here means conserve. So conserve means you don't want to change it. You want it to be conserved. You don't want to change it. So the mechanical energy will not be changed. Therefore, mechanical energy initial is equal to mechanical energy final. Now we know that this mechanical energy is the sum of kinetic energy initial plus potential energy initial. Then we also know that this is the same thing, just that it's in final. Then we know that for potential energy, there are many types of potential energy, but the case that we learned in chapter 5, it's gravitational potential energy, G stands for gravity, and elastic potential energy, the S stands for spring. So we have Kf plus UGF plus USF. Okay, so for this case over here, we have to see whether there's change in speed or not. If there is change in speed, then there will be change in kinetic energy. If there's change in height, then there will be change in gravitational potential energy. If there's compression or extension of spring, then there is elastic potential energy. So for here, I think we can safely assume that the block will change speed, because this spring here will resist the motion. It will provide some kind of resistance to motion, so the block will definitely slow down while moving to the left. So there will be change in speed. So definitely we'll be keeping kinetic energy. How about gravitational potential energy? Well, throughout the whole process, you still remain on the same tabletop. You don't change your height. So if you don't change your height, I believe there will be no change of gravitational potential energy. So this one you can remove for initial and final. The last one, elastic potential energy. Yes, there's spring compression, so you need to keep it here. So with that, we can make our equation slightly simpler by saying that Ki plus USI equals to Kf plus USF. Okay, so now we have arrived at this part. It's about time for us to substitute things, but we have to be very careful. This part, the left-hand side of the equation, is talking about the initial situation, whereas the right-hand side here is talking about the final situation. So you have to be very, very clear where's the initial situation, where is the final situation, and how does it look like, what are the parameters of it. So I believe most of you can see that this first diagram here is actually the initial condition, whereas the second diagram here is the final condition. So there are a few things that we need to know. First thing is, for the initial situation, you know that the kinetic energy will be half mv squared. The v is being indicated here. The mass is being indicated here. So you'll be safe to do it. I'll just write v because they use the symbol v. I won't change it to vi or u. Okay, then half kx square. But since this is initial case, we have to label initial for x. So what is the initial displacement from equilibrium position? That's what it means. K, if there's change in spring, then of course you need Ki and Kf. But for here, the spring is the same spring, so there's no change in spring constant. So let me just continue write everything down. Okay, so it's about time for us to do a bit of substitution. So half, then the mass is 2 kg. See, everything I refer to the diagram. When I extract my value, I refer to the diagram. V, I'm not sure. That's what I want to find. Then half K, which is 1000. Then Xi, what is the initial displacement from equilibrium position? No, there's no displacement from the equilibrium position initially. So Xi will be equals to 0. And finally, you have 2.0. What is the final velocity? Well, what is the final velocity? We are not really sure, right? I didn't label it in the diagram. So how? But first, let's think about it. They're asking us to find the velocity. Are they asking us to find the initial velocity, or are they asking us to find the final velocity? So some people might be puzzled about this, whether it's finding initial or final. But the thing is, the question itself is not really well defined. So we actually have to make some kind of assumption to make this question solvable. So the first assumption that we need to make is this 2 cm here is the maximum compression that the block can exert on the spring. So we can modify a bit the question. The block compresses the spring by a maximum of 2 cm. So if that's the maximum compression, then we know that when the block is now moving to the left, compress the spring, once it reaches 2 cm, it has reached its maximum compression. So what happens after that is the block will actually bounce back to the right, while the spring is actually restoring to its original length. So the block here will be changing its direction, moving to the right, being bounced backwards. So the thing to think about is, before this, the block is moving to the left. Then after reaching its maximum compression, it will bounce back to the right. So initially it's to the left, after final it will be to the right. So there's a change of direction going from one direction to the opposite direction. So when you are changing the direction to go from positive to negative or negative to positive, as long as you change direction to the opposite direction, there's need to have one moment where the velocity is zero. So this is a situation that you probably see in your projectile motion. In your projectile motion, at the highest point, your Vy equals to 0. Why? Because initially for this part of the journey, you are moving upwards. For this part of the journey, you are moving downwards. So we are applying the same concept here. Initially, the object is moving to the right. But after this final, it will be, initially it's moving to the left. But after final, it will be moving to the right. So there's a change of direction. So when there's a change of direction in the middle of it, which for this case is the situation where the spring is compressed maximally. So you will have final velocity of 0. Because you are in the middle of a transition from motion going to the left to motion going to the right. Because you are at maximum compression, after that what will happen is the spring will restore to its original length, so the block must move to the right. So if you change from left to right, that moment where you change from left to right, the speed has to be 0. The velocity has to be 0. So in that case, we know that final velocity is 0. So now we are able to continue with our question. Half thousand, what is the final compression? You see that is 0.02 meter square. Okay, so now if you use a calculator to solve everything, to solve for V, you end up with the answer of 0.45 meter per second. Okay, it's just calculation using calculator. So we have successfully solved question A, where they ask for when the surface is smooth, which is when the surface is frictionless. Okay, but for B, what has changed now is that the surface is now rough, and the frictional force between the block and the surface is 3.0 Newton. So there's a frictional force which is equal to 3.0 Newton. So I think it's okay for us to label it like this. Okay, so there's frictional force. So when there's frictional force, what will happen is this velocity that we see right here, right? If the block is continuing its motion to the left, what's happening is this V will decrease as it moves along until it touches the platform. Along this journey here, okay, let me be very clear. This journey here, the block will be decreasing in terms of speed. So once it's decreasing in speed, it will be compressing the spring. Okay, while compressing the spring, besides putting energy to compress the spring, there will be energy lost through friction. So before that, all your kinetic energy will be transferred to compress the spring. But now some of the kinetic energy will be lost to the surrounding as heat, because there's friction. Okay, but they still specify that you compress the spring by 2 cm. Means by you still compress the spring by the same amount. Means by you still need the same amount of elastic potential energy at the end. So if you need the same amount of elastic potential energy at the end, it means that you need to have greater kinetic energy initially. Okay, because some of the kinetic energy has to be lost to the surrounding through heat, then the rest can be supplied to the spring. If now there is energy loss, means by you need to have greater energy initially. Therefore, the speed will theoretically be higher. That's how I think about the question. Okay, just thinking. But what kind of steps can we do? Before we talk about how to solve the question, I would like to point out something. This question, right, is impossible to solve unless we remove the hand. Because if you have hand, right, you're actually exerting external force, and we don't want any external force. Having friction is enough for us to analyze really. External force will make things even more complicated. Then the second thing is, they don't tell you what's the distance over here. The distance from this block over here, look at the picture in the question. They don't tell us the distance between here and the platform. So we don't know how much decrease in speed there is when it goes from here to touching the platform. So actually this question is not solvable unless they give us this distance. But one modification we can do is we can take the initial situation to be when the block is touching the platform of the spring. Okay, means by we modify our situation to be like this. So we take our initial situation to be when the block just start to touch the platform. Only that we are able to find this velocity, and we don't need to find what is the velocity when it's at the distance away, because there will be decrease in velocity here when it moves from the initial this place to the platform. But we don't know the distance, so we don't know how much velocity will be decreasing. Okay, so let's just treat this as our initial situation, and the final we keep it the same. If you change this initial position, it will not change the answer in A, because A, the surface is smooth, so there's no change in speed when it's moving from here to the spring platform. So there's nothing changed for your initial condition. Okay, it will not change the V. Okay, so I know it's a bit confusing. But let's continue. The surface is rough. So if the surface is rough, and we know that there will be energy lost to the surrounding. If there's energy lost to the surrounding, then the energy initial will be greater than the energy final. And why energy initial is greater than energy final? Because when you go from initial to final, there's some energy loss through friction, which technically is just heat energy. There's heat loss to the surrounding. That's why your initial will be greater than your final. So what we can say here is, initially you have this much energy, this much mechanical energy, but due to work done by friction, you experience a loss in mechanical energy, causing your final mechanical energy to be EF. So this is the initial, this is the final, and to go from initial to final, you undergo certain processes. Okay, so this process causes loss of energy. That's why EI is greater than EF. So if EI is greater than EF, then this work done by friction here has to be negative. Okay, imagine if you have 5 joule here. Okay, just a rough idea. If you have 5 joule, then this one EF should be lower than E initial. So let's say you have 4 joule here. If I tell you it's a plus, then what kind of process should it be inside here? Should it be 1 joule or should it be negative 1 joule? You see that the answer should definitely be a negative answer. So later when you are solving the question, you have to see whether work done by friction is a negative value or not. If not, then you're something wrong with your working. Okay, so with that said, let's try to solve the question. Mechanical energy initial and mechanical energy final, well, it's the same situation as A actually, because we don't change the spring, we don't change the mass, we change the initial velocity, of course, but the final velocity is still the same, the amount of compression is still the same, so all the thing is being kept constant except that you introduce friction right now. But because the friction is being taken care of in this second term over here, we can just copy this first term and the third term here from this question A over here. So what I mean is, you can technically copy this whole thing here, because there's no changes to the initial and final situation. It's just that you now add on friction, but friction we take into account in the work done by friction part. So it's the same situation, so you can copy, but what's different is you need to take into account work done by friction. So let me move this over there. So we have space to talk about work done by friction. So work done by friction should be Fs cos theta. Okay, I am skipping some steps here. So what is F? Your F is 3 Newton. Where do you get 3 Newton? It's from the question. 3 Newton. Okay. Then S, what's the distance? The distance is the amount of compression that you get, 0.02. Okay, if you notice here, we start here, then we end here, we know the distance. The distance is 0.02. That's why I say you have to fix the initial to be like this. If your initial is further away, right, then you need to have greater length. But you don't know what's the length, so you cannot solve the question. Okay, then the next thing is cos, what's the degrees? What's the degree? The degree should be 180. Because again, if you look to the diagram, the frictional force is pointing to the right, but the motion is pointing to the left. That's why they are in opposite direction. The theta should be 180. So if we sub in everything and we solve for V, then you get your answer to be 0.51. Okay, the answer should be 0.51 meter per second. Okay, so I solve it using this way to try to tell you the flow of the story. But actually, if you want to relate it to the previous video, you can say work done by non-conservative forces is equals to the change in mechanical energy. Then you can say the change in mechanical energy is EF minus EI. Then this one, the non-conservative forces that we have here is friction. So work done by friction. Now if you rearrange the equation a bit, you get EI plus work done by friction equals to EF. So it's the same formula as what you apply here. It's just that I try to explain it in a more chronological flow. Okay, instead of just plugging in equation. Well, there's many ways you can think about it. You can even do it using work total equals to work done by conservative forces plus work done by non-conservative forces. You can even start from here. So you know work total contribute to the change in kinetic energy. Then work done by conservative forces, you have work done by spring. So you know there will be negative change in potential energy of spring. And plus work done by non-conservative forces, you can say this one is Fs cos theta. So if you move things around, you get, okay, this one has to be a little bit careful. Kf minus Ki USI minus USF plus Fs cos theta. This is not static friction, this is force times displacement. Okay, now if I reshuffle a bit the equation, it will be Kf plus USF equals to Ki plus USI plus Fs cos theta. So if you see here, this part of the equation is what we sub here. Whereas this left hand side, it's now this side. Okay, there's many ways to solve this equation. They are all the same formula, just being manipulated here and there. Okay, so yeah, that's how you solve a situation when the mechanical energy is not conserved. Okay, when the mechanical energy initial is not equal to the mechanical energy final, that means the mechanical energy is not conserved. Why is it not conserved? Because there is work done by non-conservative forces. That's why you do it this way. Okay, so I hope the explanation can be helpful for you to solve this kind of question. So that's it for this question. Thank you very much.